We're in 1.3, representing and describing transformations. So this section will more than any other rely on your algebra skills. So think back to graphing, x, y, coordinates, that sort of thing. But first, I want to talk about transformation. So what is a transformation? Well, it's when something changes. So my example here is Hannah Montana. Here's Hannah Montana, and then she does a transformation and she changes into something else. Um, Miley Cyrus is very different than Hannah Montana, um, but essentially it was the same thing, right? There's continuity there. Ship of Theseus, if you're into philosophy. So we're going to do the same thing with our little shapes and points and things like that. So um, for our terms, we're going to call a transformation anything that changes the position, shape, and or size of the figure. So our original figure, it's a little weird, our original figure is going to be the pre-image. So have you guys ever read like a prequel, for example, like Star Wars prequels or something like that? A prequel happens before the normal one, right? So a pre-image happens before the normal image. So we're going to start with our pre-image. This is Hannah Montana, and then we're going to do some kind of transformation, and we're going to end up with our image, our Miley Cyrus here at the end. Of note here, we can use these little prime tick marks. So the original pre-image will be just a plain old A. Once we transform it into an image, we'll have a little tick mark here. So it's sometimes called A prime. We can go even further here. Let's say I do another transformation of some sort. I'll just move it over here, I guess. I've moved it over here in another transformation. What's the name of this point? Well, it's A prime, and then I did another transformation, so it's A double prime. Whoa, cool. Okay. Just of note, we'll be in the coordinate plane here, so we'll do some transformations in the coordinate plane. Up here is our, it's called coordinate notation. Yeah, is our coordinate notation for this transformation. So all points in the coordinate plane have an x and a y, right? You guys are used to that. You do the x first, you put a comma, and then you do a y. So we're going to do this point, whatever it is, with a nice happy xy. That was the original pre-image. And then we're going to transform it using this arrow, right? That arrow represents a transformation. And this is how we're going to transform it. We're going to take the x and we'll subtract 4. We're going to take the y and subtract 3. So the book has some examples here. We'll call point A, this point there. It's at the coordinate 0, 4, right? 0 on the x-axis, 4 on the y-axis. You guys with me? Good. I know it's like stuff from last year, but you can probably do it. We're going to apply our transformation, right? So we're going to subtract 4 from the x value, so 0 minus 4. And then we're going to subtract 3 from the y value. So that's 4 minus 3. Note here we keep our comma, and we basically just do this little math equation right here left of the comma, and this little math equation right here right of the comma. Very similar to like midpoint formula. So we do our little equation. 0 minus 4 is negative 4. 4 minus 3 is 1. Therefore, A prime is at the point negative 4, 1. So here's A prime, negative 4, 1. B, we'll do the same transformation for B. So where does that one end up? Well, minus 4, minus 3. Pause here for just a sec while you go ahead and answer these questions here. Okay, 3 minus 4 is negative 1. 0 minus 3 is negative 3. 0 minus 4 is negative 4. And 0 minus 3 is negative 3. So these are the coordinates for B prime and C prime. Note here that the triangle basically just shifted, right? You took a triangle up here and it just scooted down. it scooted 4 units left and 3 units down. So it was a translation. Here, a little confusing, there's two T words. There's a transformation, that's when anything just changes, right? Transforms. A translation is when we just slide something left, right, up, down. So we don't change the angle, we don't change, the overall shape or anything like that. We just go like, think of like Frogger or something like that, right? You can go forward, you can go left, you can go down, you can go right, up, down, left, right, up, left, down. You don't like totally morph it and change it in any other way. So translation went 4 units left and 3 units down. The size and shape are both preserved here. Sorry, answer got cut off. But same size and shape, right? Okay, we'll do this other transformation. So this transformation, what we're doing is we're taking the x and y coordinates, and now the x becomes negative. And we'll see what happens here. So go ahead and pause here. Okay, we make these x values positive, so we got +4, +1, +4, and then the same x's, same y's. We don't change the y's at all. So therefore it makes that. If you were to graph it, it should look something like this on your graph. This is a reflection. So just how you have a reflection in your mirror where your left hand is looks like your right hand and stuff like that when you mirror it. In this case, we're going to have a mirror image, right? So there's no way to just scoot that original shape up, down, left, right. What we have to do is we have to just like reflect it all the way around. So in this case, we're reflecting it over this y-axis. We'll go into more detail on these later. Don't worry about it. For now, you just need to know kind of how to apply these transformations when they're given. So for example, at point S became S prime over here, point R reflected over here, and point T reflected over here. Is it the same size and shape? Yes, it's the same size, same shape. Of note, it's a slightly different orientation, right? It's mirror imaged. There's cool applications when you get to like chemistry and things like that. You can have a molecule and then a mirror image of a molecule, and they may be chemically the exact same, but functionally, like when you ingest them into your body may actually process them differently. There's some cool things with that. Okay. This transformation, what do we do with this transformation? Well, this one we're going to multiply the x value by 2. Go ahead and figure that one out. And I'm just deleting all these. We multiplied all the x values by 2. Again, the y doesn't change at all, so the y's are totally constant. And when you graph it, is it the same size? Well, no. Is it the same shape? The same general shape maybe, but in this case we'll call a fat triangle a different shape than a skinny triangle. So no, it's not the same shape. Even though it's in roughly the same spot, it's still moved around a little bit too. So it's twice as wide, but the same height. So it's kind of like a stretch, right? We took each little corner and stretched it out. And we talked about those already. Yep. So the image and the pre-image are both right triangles, but they don't have the same size and specifically the same shape. Right? They're both right triangles, but they're different right triangles, right? The angles aren't the same. Okay, so those first two we're going to call rigid motions. So rigid motions are motions that preserve distance, angle measurements, betweenness. There's a couple types. There's the translation, right? That's the one that moves it left, right, up, down. Think of the Frogger one. That's a rigid motion. The shape doesn't change, the size doesn't change. The second one is a reflection. We talked about that one. You have like a little reflection, one mirrors over onto the other. So it's a perfect reflection. Whoop, look at that. The third one is a rotation. So if I take something and I rotate it, the size doesn't change, the shape doesn't change, just the angle that it's at changes. So those ones are rigid motions. And these are some properties of rigid motions. So here's its rotation example. It doesn't go into detail on it, but basically it took this image here, it rotated it around there. So it's asking, is this a rigid motion? The really headachy way to do this is to say, okay, well, are all the lengths the same? Are all the angles the same? You don't have a way to calculate these angles besides using a protractor, so feel free to use one. But we can also check the lengths. The easy lengths would be AB, that's 3, A prime to B prime, well, that's 3 too. You could do, we need to check, the other lengths as well. We can go B prime to C prime, and sure, you could do what they do down here and go use the distance formula, and it's the exact length, and yes, that's correct. It's how you use the length, or how you find the length of a segment. However, again, there's an easier way. It's the counting method. Since we're in the coordinate plane, we can merely count the distance both horizontally and vertically. So if we're going from B prime to C prime here, we'll go 1, 2, 3, 4 units to the right, 1 unit down. If we were to go from B to C, right, this is the corresponding side we want to check. We're going to go 1 unit to the right and 4 units up. 1, 2, 3, 4. So is 1 unit to the right and 4 units up the same length as 4 units to the right, 1 unit down? Well, I'll prove it to you using the Pythagorean theorem here. Basically what they're saying is, which one are we doing? BC. So this is the 1 unit, right? This is from B to C, it has a horizontal change of 1, right? So they're going to do the horizontal change of 1, square it, add the vertical change, which is 4 squared. So what is 1 squared plus 4 squared? Well, it's 1 squared is 1 plus 16. So 1 plus 16 is 17, right? When it comes to B prime and C prime, this time the x's have a difference of 4. So we square that and get 16. The y's have a difference of 1. We square that, we get 1. 16 plus 1 is 17. So it doesn't matter if you do the x's first or the y's first. Remember this addition, it doesn't matter what order we add things in. So that's kind of why it comes out that way. Is that, this is a triangle that is 4 by 1. This is a triangle that is 4 by 1. Therefore, the hypotenuse of both these right triangles is the same because they have the exact same length. This, to me, is enough information that these two lengths are the same. If you say this is 4 by 1 and this is 4 by 1, to me, that means, yes, they're the same length, they're done. You should know how to do the distance formula and how to calculate that, but it's not necessary for this problem. And then it tells you to measure the angles. And yes, all the angles are the same, all the side lengths are the same, so therefore they're the same triangle. It is a rigid motion. Okay, we'll look at this one. We'll do another pause. Here. Boink, boink, boink. In this case, you're going to discover as you walk through this one. I left this image up here so you can see it, but this one is a reflection over the x-axis. And we can check to see if this is a rigid motion. Again, the segment that goes just left and right here is easy to do. We can count. That's 1, 2, 3, 4, 5, 6 units. This one is 1, 2, 3, 4, 5, 6 units. So we're good there, 6 and 6. Again, you can use the Pythagorean theorem for, say, QR here, but I'm just going to count. So this is 1, 2, 3 down and 2 over. 1, 2. Thanks, dear. This one is 3 up. 1, 2, 3 and 2 over. 1, 2. So is a 2 by 3 triangle the same thing as a 3 by 2 triangle? Yes. Since these are both right triangles, the hypotenuse to both of these is the same. So RQ, this one, RQ is equal to R prime to Q prime. So therefore those are equal. And then finally we can do another check here. 1, 2, 3 by 1, 2, 3, 4. So this is 3, this one's 4. 1, 2, 3 by 1, 2, 3, 4. So that one's 3, that one's 4. Therefore, the hypotenuse of both of these guys is the same as well. Then you can measure the angles. I'm going to erase these so you guys have the numbers, but don't feel like you have to write in every single one of these. It's kind of busy work, and if you understand this and you don't need to write all this down, please don't. I'm not going to grade you on it. Boink. But if you do want to write it down so you can go back through these notes later and understand what's going on, that's fine. The boxes get a little confusing, but yeah, they're just little boxes where you write in numbers. So in this case, it's 1 minus a negative 3. And then square that value. 1 minus negative 3 is 4. 4 squared is 16. We're going to add 16 to, what's the difference between negative 4 and negative 1? Well, it's 3. Negative 3. And then you square it. So that's 9. 9 plus 16 is 25. And the square root of 25 is 5. So you can, again, feel free to do the distance formula, get answers. It's good practice. You don't need to do it for these problems. Okay, I have a few more examples here. I'm just going to reveal the answers to you here. I'm not going to walk through them all, but I just want you to be able to, oh, I should pause or something. Did I do this one? I think I did. Answer that one. And yes, they're both rigid motions in this case. In this one, if it's not a rigid motion, it will have some kind of coefficient here. So it's basically going to multiply either the x or the y by some value. In this case, we can look and try and figure out what that pattern is. Some folks are pretty good at pattern recognition, others aren't. But we can kind of look and see, oh, you know, how did these change? How did this change? How did this change? The first thing you'll notice is that the x values don't change at all. And then when you look at the y values, you may notice that we're just multiplying them by 3. So you should be able to determine this. We'll do more practice with this later too. They go ahead and work out some of these lengths, but note here, because of the coefficient, we're doing we're multiplying the y values by 3, so therefore we're stretching it vertically, and the lengths will be radically changed by that, since it's 3 times larger. We'll do a picture here. Again, in the interest of time, I'm not going to go through all these. Oh, this one doesn't have a picture. It should have a picture. I encourage you to try and work through these and figure them out before I erase everything. I showed another pause screen there. All right, there you go. Oops. That's boring. Okay, go ahead and see if you can figure these ones out. Again, there's no image, but feel free to get some graph paper and draw the images and pre-images in order to kind of visualize what's going on here. But we can just look at the patterns algebraically too. So pause here. well, what's the pattern between these guys? Well, oh, hey, the X and Y are both getting bigger, right? The X and Y are both getting bigger. The X and Y are both getting bigger. But, then how much are they getting bigger by? Turning 2's into 3's and 4's into 6's. We're multiplying it by like 150%, right? So we're multiplying it by 1.5 or by 3 halves for both of those. Okay, so we make everything really big. We can check the lengths here. They go ahead and use the easy ones. Once you find one pair of corresponding segments that does not preserve length, right? So if you find that AB is equal to 2 and A prime to B prime is equal to 3, we can stop there. We don't have to check all the other sides, because as long as one side changes length, then we know it's not a rigid motion, right? All three have to be the same in order for it to be a rigid motion. Same deal on this guy. Oh, I just gave away that. You didn't see that. Oh, whatever, doesn't matter. So note here that the x's are being halved. The y values are being tripled. So therefore, we're really, when you graph this, you'll notice that the x values shrink, so therefore it squishes in, and then it becomes even taller. So it's like a super skinny, tall version of itself, and it's not a rigid motion as a result. Okay, that's all I got. Go have fun, no more homework.